I am Anil Kumar. Welcome to my series on advanced functions. We'll discuss polynomial inequalities in this particular video. Here are the key features which we'll take into consideration. We'll begin with the very basic concepts of inequalities. We'll see how to represent a solution of a inequality in interval notation. We'll learn about linear inequalities and their solution on number line. We'll solve polynomial inequalities with graph. We'll also provide algebraic solution, analyzing the situation using factor tables. And then we'll also pick up, as we move along, questions from previous test papers. Some of them will be communication and thinking applications. We'll consider extended application to higher degrees. To begin with, whenever you find a symbol which is kind of like this, or like this, or maybe combination with equal to, but greater than or less than, we are talking about inequalities. Let's write down their meanings. This means less than. That means greater than. And we have combined, so it is less than or equal to. And this is greater than or equal to. The term and or are very critical while we are working on this unit, since it will make huge difference, right? Let me show you with an example here. We have a graph, for example, and if I want to say, let us say this is a function for us, we name this as f of x and the other one as g of x. So this we are calling as f of x, and here this one we are calling as g of x. Now if I have to represent a solution that g of x is greater than f of x, in that case what are we looking for? We are actually looking for areas where the graph of g of x is higher than the graph of f of x, right? So the region which we are really looking for is, you can note from here that this cubic function is greater than the linear function in the region which is on the left side of -3, on this side, correct? Or which is in between these two values. You get the idea. So only in this interval, not including these values. Now let's elaborate on the basic concepts. So you have learned that these symbols make a huge difference. Let me now sketch another graph for you. And what you need to do here is to figure out what is the interval of our interest. So let us say we have an equation which is y equals to x, and then we also have an equation which is y equals to x squared. So if I sketch these graphs, then y equals to x will be a line which will go through the center, and y equals to x squared, on the other hand, will be a parabola which could be drawn like this. And now let us try to shade the region where, since I gave both names of y, we will say now region where x squared is greater than or equal to x. So when we say x squared is greater than or equal to x, that means we are interested in the part of parabola which is above the line. This part we are interested in, right? which is this part we are interested in, which you could also shade as these are your point of intersections, right? So we are always interested in the x values, which is right here. These are included this time since we have greater than equal to. And the region which is of our interest is where x is less than equal to 0 or x is greater than equal to this point of intersection, which is going to be 1 on the graph. Does it make sense to you? So that is how you have to look at the situations. Perfect. There might be examples where we have intersecting lines. So let me just draw two lines now and then we'll discuss. Let's say one line is kind of like this and the other line is kind of like this. Let's give them different names here so that it becomes easy for us to communicate. Let's say this is our function f of x and the other one is a function g of x. So with that, I hope you also figure out that naming or using function notation is a good concept. Now, if I have to shade the region where f of x is less than g of x, in that case, what will be the interval? Now, let's do two things. First is shading. So f of x is less than means we are interested in the portion which is, this is the point of intersection. The green line represents f of x and it is below the other line beyond this point. Let's call this point as A. So the region will be after this, right? So everything after this is your interest. Now it does not include the line and therefore we'll write a dotted line here. So this dotted line indicates that all the points on the line are not included. Do you understand? So you have to be very careful about the sign which we are using. We're not using equal to, and therefore the interval will not include the line itself or the point of intersection. And our answer in this case will be that the value of x has to be greater than a for this to be true. Does it make sense to you? Perfect. So with that in mind, let's move forward and take some examples. Now, it is very important to write down the answers correctly, and therefore I've introduced this unit in between, inequality and interval notation. There are different ways in which you can provide solutions, and we'll talk about open interval, closed interval, and infinite interval. Now, let me show you on a number line all these intervals and then we'll move forward. Let's say this is our number line. Many times we are providing solutions on the number line itself, especially when we are dealing with the linear inequalities. Now, on an open interval, we're trying to say that the solution is between these 2 points A and B, and that is open. So this is A and B. So it is in between A and B as shown here. Points A and B are not included. That is open interval. If I want to close the interval, then we will fill in this gap like this and then consider the interval. So this is between A and B closed interval. Does it make sense? It includes point A and B. Infinite interval could be something like this. We have from here but less than. Do you see that? This arrow indicates that we are going towards minus infinity. So that becomes an open interval. It could be open infinite interval. So moving towards the infinity, not bound. or something like this, right? So we could use symbol A and B as shown here. Now the same thing can also be represented in many other formats. Interval notation will be normally used when we say open interval. We use the brackets like this. We say from A to B. Brackets, they represent the open interval. For closed interval, we will use the square brackets. So A, B will be a closed interval. Whenever you're using open interval with infinite limits, in that case, infinity cannot be contained, right? So it is minus infinity in this case to A. Does make sense to you? Now here is an open space in between also, and we are looking into connecting two portions. We use the word union, or we could write or we could even write a comma there. And then from B is not included in this case to infinity. So that is how we are going to represent on interval notation. Now the same thing can also be written in inequality notation, where we are assuming x is our variable and this is between A and B. So if we use the sign greater than, in that case we have an open interval. However, if I use greater than equal to sign, which is x is greater than equal to A and less than equal to B, it becomes a closed interval where A and B are both included. For infinite interval, we will use the combination where we say x is less than A. We are using less than since it was open A, right? We can use comma here, or x is greater than B. So with a comma like this. So these are the correct ways of representing inequalities. So whenever you have the symbols written, they have to point at the same side. You cannot have a combination. For example, writing, uh, sometimes this particular region, students may say x is maybe, I'm just writing like this, C, and like this, D. Now that is absolutely incorrect, right? So this avoid. So it is mistake, right? Do not do this, right? So these are the correct ways of writing, all pointing in the same direction. Is that clear to you? Let's move on and take up some examples. So the very first question for you is express the intervals in terms of inequalities. So the first one is an open interval, infinite interval, closed interval. So you can pause the video, answer this question, and I'll just write down the answer. So we'll write down x as in between 2 and 5. So we'll write this as x is between 2 and 5. Is that clear to you, right? The next one is from minus infinity to 1. So that means x is less than and equal to 1 because of the closed bracket. Now this time both brackets are closed. So we are saying that x is in between two values which are minus 3 and 5. Perfect. So that is how you're going to do it. Now, as an added exercise, I will add two columns for you. I would like you to write this in the form on a number line, right? So represent them on number line. So let this be your exercise. Is that clear to you? Let's take up the next example, question number 2, which is express each of the following in the interval notation. So now we have to write in interval notation. We are already given the inequality, right? Greater than and less than types. So when we are saying x is greater than 5, then 5 is not included. So we'll write 5 with this kind of a bracket, and greater than has got no bound and it is infinite. In between two, both included means square brackets with the limits. And this is when x is less than 0. X is less than 0 means it goes up to minus infinity from 0 both are not included, or x is greater than 3, that means it goes from 3 to infinitely large value. Is that clear to you? So that is how you have to write your answers. Now here is a question which is based on linear inequalities and number line. What I'm trying to say here by number line is that you have to represent your solution on a number line, right? That's what I meant. Okay, so the question is solve 2x minus 3 greater than or equal to 7. So the question here is we have 2x minus 3 and that is greater than or equal to 7. So it is to be solved like equations. We'll bring 3 to the other side and we say 2x is greater than or equal to 7 plus 3. We can say 2x is greater than or equal to 10. Dividing by 2 both sides, we get 10 divided by 2. Our answer, which is x, is greater than or equal to 5. Now to write this solution on a number line, we'll just draw a number line as shown here, and we know x is greater than 5. So in that case, we'll mark 0. 5 is on the right side and it is included, so we'll make a solid circle and an arrow, writing 5 at the point. So that indicates the solution. Is that clear to you? Perfect. Now, let's do the second question, which involves fractions. So it is half of x plus 1 less than 5. So let me write down here half of x plus 1 less than 5. So we'll take 1 to the other side and we say half of x is less than 5 minus 1, and then we say x is less than 5 minus 1 is 4, and we are multiplying this 4 by 2, and we have our solution that x is less than 8. So I've combined few terms here, few steps, which is not a good idea, but sometimes it can be done, right? So I will prefer to use this, which includes all steps. This is better. Perfect. Not this, right? So this is not preferred. Okay. Now anyway, it is not wrong. Sometimes you could do it. So x is less than 8. This time will mean here we have a 0 and 8 is somewhere there which is not included and the arrow is pointing towards the left side. Is that clear to you? Simple but very important concepts to understand. Let's move on. Question number 5 here is 5 minus 2x over 3 greater than or equal to 9. So let me rewrite this. We have 5 minus 2x over 3 greater than or equal to 9. So first step is we'll multiply by 3. So we get 5 minus 2x is greater than or equal to 9 times 3. So that gives me 5 minus 2x is greater than or equal to 27. Now, here we have minus 2x. We'll see how to work with that. First, let's take care of 5. So we get minus 2x is greater than or equal to 27 minus 5. And that gives you minus 2x is greater than or equal to 22. Now here you have to divide by minus 2. Now this is a very critical step which I really want to elaborate on. So I'm rewriting here minus 2x is greater than or equal to 22. Now we have to divide both sides by minus 2. So what happens now? If I'm going to divide by minus 2, that is to say divide by minus 2, then the sign will change. So important note here is multiply or divide by negative number results into change of sign. Now, this is extremely important. Now, it creates a lot of confusion, and let me give you an example here. 7 is greater than 5. How about minus 7 and minus 5? You have to change the sign. Does it make sense to you now? So that is key to understand. So I have multiplied by minus 1. I have to change the sign. So minus 7 is less than minus 5. Perfect. On a number line, on a number line, if I have numbers, then this is, let us say, minus 7. This is minus 5. That is 0. And this is 5. And this is 7. So on a number line, greater numbers are on the right side. Do you see that? Does it make sense to you? This is very important. That is why I'm emphasizing so much a common mistake seen in so many test papers. So when you divide, you get your answer, which is x is less than equal to minus 11 because you're dividing. And that becomes the solution. And on a number line, you're going to show this like this. So less than, so let's say this is 0 for us, and we're looking for minus 11, and the solution is on this side. Is that clear to you? Perfect. Now, here is another thing to consider, and let me put this as a tip. Now, tip for you in this particular case is at this stage, instead of taking 5 to the other side, so let me write from here. At this stage, what we could do is we could do 5 minus 27 greater than equal to 2x. Do you get the idea? If you do that part, then you don't have trouble of fixing your sign. So at times, that may be a better idea. Is that clear? So we also prefer this to avoid confusion at this stage. Perfect. So you could actually take the x term to the other side, keeping the coefficient of x positive. That's the whole idea. Okay. Let's take the next example, which is question number 6 for us. Graph of a cubic function f of x and a linear function g of x is given to you. So first and foremost, this is cubic function, which is f of x, and linear function, which is g of x. Write the interval in which we want to find f of x is less than g of x. So you can actually pause the video. We answered this question earlier and write down your solution. We're always looking at the point of intersections. Does it make sense to you? We're looking at point of intersections. So these point of intersections are at what value of x? So they are at this value of x, correct? Now these values are not really included in the solution. Perfect. So our solution will be, I'll write on a number line this time. So let us say we have, okay, I'll put 0 on the left side since most of the points are on the left side. So I'll put 0 slightly ahead on the right. So we have these points which are, let me mark the points first. So we got 3 points, which is, these are the 3 points for us. So this is minus half, this point is minus 1, and then here we have a point which is 3. Those are the point of intersections. And we want to know when is f of x less than, that means below the line, correct? Below the line. So basically, we are looking into this particular interval. Let me highlight this with a different color. So this portion is below. Clear? So that is the interval which we are interested in. And now we can show it on the number line itself. So f of x is less than g of x when it is in between 3 minus 3 and minus 1, or it is after minus half, and the point of intersections are not included. Does it make sense to you? That is how we are going to write our answer. So this is our answer. You could also write this in other forms, right? So solve polynomial inequality with graph, and we have not mentioned, so we could write this also as in between minus 3 and minus 1 union minus half to infinity. Is that clear to you? Or we could say x is greater than minus 3, less than minus 1, or x is greater than minus half. So these are three different ways of writing your solution, right? So this is one solution, this is second, and third. All are exactly same, representing the same answer. Perfect. So that is how you're going to represent the solution. So let's take quadratic inequality now. The question here is solve polynomial inequalities with graph. Solve x squared minus x plus 7 greater than or equal to 1. So let's rewrite the question here, which is x squared minus x plus 7 is greater than equal to 1. So let's simplify this. X squared minus x plus 7 minus 1 is greater than equal to 0. So that is x squared minus x plus 6 is greater than equal to 0. 6 is can be factored. We need minus 1 here. So 6 minus x minus 3, 3 and 2 will work, right? And x plus 2 should be greater than equal to 0. So that gives you two zeros, the x-intercepts being 3 and so let's write down x-intercepts are at x equals to 3 and at x equals to minus 2. Let's sketch this parabola since the question is with graph. So here we have a parabola which is having two x-intercepts. It opens upwards. So let me just sketch the parabola and then we'll look into the solution also. So it has two x, one is at minus 2 and the other one is at 3. So we'll sketch a parabola and we know that the two x-intercepts are at minus 2 and at 3. Now the question here is, we're looking for a value which is greater than equal to 0. So greater than equal to 0 is beyond these points. So parabola is above the x-axis in this interval. Does make sense to you? And therefore, we get our answer, and that is x is either less than equal to, and these points are included since we have equal to there, right? So less than equal to minus 2, or we can write comma, x is greater than equal to 3. Does it make sense to you? That is how you have to do it. On a number line also, you could represent your solution. So if I have a 0 here, for example, then on a number line, less than equal to minus 2 will be here with a solid circle filled in, and greater than equal to 3 with a solid circle as shown here. So that is how you would actually show your answer. Sometimes you need to shade the portion, correct? If you have to shade the portion, then that could be the shading done, right? So that is what we're looking for. So on a particular line, this is the interval, and the graph will also be included in the shade. So the graph will be included as we shade. So that could be also done. So that could be also done. Does make sense to you? This is what is your result. Let's move on and take the next question now, which is question number 8. Solve polynomial inequalities by graphing. So we still have another example with graphings. The question is 2 times x minus 1 times x minus 3 times x plus 2 whole square greater than equal to 0. Let us see how to sketch this polynomial. So first we'll look into the x-intercepts. So what are the x-intercepts for us? Here we have x equals to 1, then we have x equals to 3, and we have x equals to minus 2. Now each x-intercept, I should say 0, uh, we actually call them 0. Let's look into the multiplicity. So here there's only one linear, and this is quadratic, right? So quadratic in nature. That means it will bounce back. The end behavior is that it is degree of this is 2, 3, and 1, 4. So it's an even degree function, right? And both sides up. So leading coefficient is positive. So therefore, both sides are up, and that is what we call end behavior. I'd like you to look into my videos on graphing polynomials to understand these steps if that is a problem. Okay, so now let's quickly sketch this. So we are making a very rough sketch. You can find the y-intercept for more accuracy. Now, when we are solving for inequalities, that is not a must. However, when we write graphing, that could be required. Perfect. So let's find the value. What happens when x is equals to 0? So that is y-intercept. So when x is 0, we get 2 times minus 1 times minus 3 times 2 square, which is 4 times, first is the sign. So it becomes a positive thing. 2 times 3 is 6, 6 times 4 is 24. So we have positive 24 as your y-intercept. Okay. So the x-intercepts, or the zeros in this case, are at 1, 3, and minus 2. So this is, let us say, minus 2 for us. And let's say this is 1, and then 3. The end behavior is that the graph is upwards, and at minus 2, if I look at it, is bouncing back, and at the other points it will go down and then come up. Now based on this, I can actually sketch my graph. So let me sketch this graph now with a different ink. So we'll use okay, let's see this. So we can sketch the graph of our polynomial kind of like this. Perfect. And as we are saying, the y-intercept value here is at 24. So this is your y-axis, and that is your x-axis, 0 right there. Now let's look into the inequality. We are interested in finding greater than equal to 0. That means the points are included in our solution. And the graph is above when we're looking into this interval. Sorry. Not this portion. Correct? So the graph is above the x-axis in the interval shown, right? So you could write down the solution, which let me write down here now. Answer for this will be from minus infinity to this point, which is 1. And then it is from 1 is included. And then from 3 to infinity. Is that clear to you? So that is how we have to write down the solution. And on a number line, let me redo. From minus 2 to left, include minus 2. And then also it extends to 1 since it bounces back. So it is basically from here, everything, right? Everything. Okay. So from 1 and from 3 onwards to infinity. So that becomes the solution on a number line. Perfect. So that is how you're going to show the solution. Now let's take the next example. It says algebraic and factor table to solve polynomial inequalities. So now we'll understand the algebraic method of solving. We have the factored form, not fully factored though, x squared minus 1 times x minus 3 is greater than, let me make this as 0. Okay, is greater than 0. So we'll just simplify this and focus on the technique of doing it. First step is fully factor it. So it will be x plus 1 times x minus 1 times x minus 3 is greater than 0. So in any polynomial while you're working, it is good to put all the terms on one side and 0 on the other side. We kind of changed the question. It was a typing error actually. So this becomes your factored form. Now, we know that we have zeros at x equals 2, minus 1, plus 1, and plus 3. Only at the zeros the sign changes. So the important thing here is sign changes at zeros only. Perfect. It may or may not change. If it has an even degree 0, it will not change, right? So that is kind of important. So what we need to do is we need to check intervals. So that is the concept. And how do we check it? We check it with the help of a table. So this is your method of checking. So let's make a table now. So here we'll actually work on the zeros and the intervals. So what we have is list all the zeros here. Zeros are from minus 1, 1, and 3. So these are the zeros. These three zeros divide the plane in intervals. We have four intervals. So the intervals here are, this is the interval from minus infinity to minus 1. This is from minus 1 to 1. Then we have 1 to 3. And then we have 3 to infinity. Four intervals. In each interval, you should take a test point. So the test point could be any point, any convenient point. So let's write down our test points now. In the interval from minus 1 to minus infinity, minus 2 could be a good point. Here, 0 is a good point. Then we have 2, and we can take 4 as our point. Now, at each test point, we have to see what happens to our factors. So the factors here are x plus 1, x minus 1, and x minus 3. So for each one of these factors, we have to check the sign. For x plus 1, if I substitute minus 2 here, if I substitute minus 2 for x, minus 2 plus 1 is negative. 0 will make it positive, and these will keep it positive. For x minus 1, these will be negative, and those will be positive. For minus 3, do you see a pattern also? So if you have linear factors, that is the kind of pattern you see. Now when you multiply three negatives, you definitely get a negative. Two negatives when multiplied give you positive, and that is the end result. We are saying greater than 0. That means we are looking at the solution where when multiplied, you get a positive number. So that becomes your solution. Do you see the analysis? So we can say that the function f of x is negative, positive in the given intervals. And now we can write down our solution. And that is that we are now looking at two intervals which are between minus 1 and 1 or beyond 3. Does make sense to you? Or you could write this on a number line as we have done in some cases. So we have from -1 to 1 and then beyond 3. Perfect. So that is how you're going to solve it. So once again, when we are solving algebraically, then you have to bring all the terms to the left side, factor them. Once you factor, find the zeros, and then make a table. On a table, remember, if n are the number of zeros, then n plus 1 are the intervals. In each interval, select a convenient point to test your values for each factor. Multiply the factors to get positive or negative sign. If you're looking for greater than 0, it means positive sign, and that becomes part of your solution, just as we did here. Perfect. Let's move on and take the next example, which is solve the following inequality using two different methods. So now we could use many ways of doing it. It says two different methods. Let us see how can we do uh, a solution with two different methods. So the example here is x cubed minus 3x squared greater than equal to x minus 3. Well, you could use algebraic method, you could use graphic. So two methods could be, you could have a graph solution, you could have algebraic solution. Now I will show you a third method here, which is interpreting the lines or the equations in different ways. So what I'm going to do here is basically solve two different equations. One is given to us like this. We could also think about bringing all the terms together. We have x cubed minus 3x squared. Bring it to one side, so we get minus x plus 3 greater than equal to 0. So we'll solve this equation. And on the other side, we'll focus on the equation given to us, x cubed minus 3x squared is greater than equal to x minus 3. So those two equations, we'll treat them differently. So here, what we are getting is, we can factor out x squared, so we get x minus 3. On the other side, we have x minus 3. Okay, that's interesting. So we just factored out and we have x minus 3 and x minus 3. Okay. Now, let's sketch the graph and then find the solution. X minus 3 is a straight line, and x squared x minus 3 is the cubic function. So for a cubic function, we have a 0 here. This is for x, and then for 3, we'll have another 0 at 3. And so, approximately, we know that this is a turning point for the cubic function, right? X squared, so it will turn here. The leading coefficient is positive. So the right side is up. So right side is up, and so this side is down. So we get a graph which will be kind of like this. So this is the graph of the left side. Now for the right side, let me sketch a graph. We now have x minus 3. So the graph for this particular function will go through x minus 3, let's say minus 3 somewhere there. We're not very sure where this minimum is, but let's say somewhere. Okay, let's say this is minus 3 for us. But if I write x equals to 3, I get a 0, so this point is matching. So I'll have a line which will be kind of like this. So on a graph, this will be my line x minus 3. We are saying that the interval is between greater than. So we want this red line to be above, and therefore the solution is in this interval. It is above, and we need to find this point here and this point here in between these intervals. So on a graph, you can read these points and get your solution. So on an accurate graph, that is how you are going to get the solution. Perfect. Now, let's do it the algebraic way also. So here we have x cubed minus 3x squared minus x plus 3 greater than equal to 0. So that gave us a hint that we could actually factor this taking x minus 3 common, right? So we'll do group factoring, and we have x squared x minus 3 minus x minus 3, which is greater than equal to 0. So x minus 3 is common factor, so we get x squared minus 1 greater than equal to 0. And that gives you three factors, which is x minus 3, x plus 1 times x minus 1 greater than equal to 0. So that equation, you can actually from here sketch a graph or do the interval table, correct? So both the things can be done. So what I will do here is kind of mix and match. So we'll just plot the points on the table. We have our zeros, which are at 3, plus and minus 1. So minus 1, 1, and 3. So these are our zeros. These zeros, as you see, divide us in an interval, and the factors here are x minus 3, x plus 1, and x minus 1. We can take the test points in the intervals to solve. The test points in this case could be minus 2, 0, 2, and 4. Using these test points, we can plot the values. So minus will make this negative for all of them, and that becomes positive. With x plus 1, this will be negative, but these become positive. With x minus 1, these will be negative, and that becomes positive. So when you combine them all, you get your answer from the table, which is negative here, positive here, and this is negative again and positive. So clearly we are looking for greater than, that means positive, correct? So we have the solution which is within this interval, correct? As shown here. You could actually plot your graph on this itself, and then we'll just plot it and show you what exactly we mean. So this is method number one which you've done, and the second method is this is a cubic function, right side up. These are your three zeros. So when the right side is up, then the graph will be going through these zeros. So clearly you get your answer here, and that is from this side, right? So greater than equal to and these 2 points, which matches with our solution, correct? And therefore we can now write down our answer, which is, let me write down here answer. Since we now got our points, the points are between minus 1 and plus 1, both included, minus 1 plus 1, or beyond 3, but 3 is included up to infinity. Perfect. So that becomes your answer. These are the two methods which I have shown you on the right side, which can be used, but this is also a technique, graphing technique, which I'll say third method. But for the third method, you need accurate graph to get the result. Let's move on. We are almost at the end, 4 more questions to go. Question number 11 here is, explain why the following strategy fails to solve the inequality. Provide correct solution. So the key thing is it fails. So there's something wrong here. Okay, let's look into the strategy itself. X minus 3 times x plus 1 is less than or equal to 5 minus x times x minus 3. And then next step, x plus 1 is less than or equals to 5 minus x. Now what is wrong here? Well, these terms have been cancelled to move on to the next step. So that is a mistake. So you cannot cancel terms. The reason is that x minus 3 can be negative. So if it is negative, then what? You have to change the sign, correct? Do you get the idea? Cannot cancel terms because x minus 3 can be negative. You can only cancel terms if both are positive. Perfect. And therefore, this is not the correct solution. Now, we need to now provide the correct solution. This is kind of very, very important concept. So let me highlight this. So how are you going to do it? So let's redo it. Basically, we'll have to bring all the terms to one side. So the solution will be, we have x minus 3 times x plus 1. Bring all the terms to a minus 5 minus x times x minus 3 is less than equal to 0. Does make sense to you? Just bring them together. Now you could factor x minus 3 and you get x plus 1 minus, so minus 5 plus x, we just change the sign, and less than equal to 0. So we get x minus 3, and in this bracket we have minus x plus x is 2x, and minus 4 we have, right? So you could further factor actually. So we have x minus 3 times 2 times x minus 2 is less than equal to 0. So we get our solution. Now since we have very less space, we'll just graph this and provide the solution. It is positive. So x minus 3 and minus 2, two zeros. Both the zeros are on the right side. So we'll just graph like this. The zeros being at 2 and 3. We are looking for something which is less than 0, and therefore the solution is in this interval. And we can now write down our answer as between 2 and 3. Perfect. So that is how we are going to write. So definitely this answer you can see is incorrect. Less than equal to 2. No, it doesn't work. So that was wrong answer. So now I think what you've got is the correct result. So the idea here is not to cancel the terms, bring them together. So when we brought 5 minus x and x minus 3 to the left side, we took x minus 3 common, and then what we were left with was another factor. When we combined them, we get 2x, 2 as a common factor, and that is the term which we got. And you could do with interval section also, or you could do as we did. So you have a parabola which is turning towards the left side, and you do get a result which is very different from what was mentioned earlier. Perfect. Now the good idea is to test your point. So we have a zero test. So the idea here is 0 is not in our solution. So if I put 0 here, what happens? So if I put 0 here, I get minus 3 times 1. So we get minus 3 times 1. And on this side, we get 5 times minus 3. So this is minus 3, and that is minus 15, and therefore this is greater than, and therefore we know that this is not a part of solution. So that is a check. So 0 is not solution. So since 0 is not a solution, it is outside, this says inside, we know our solution is correct. Is that clear to you? So that is extremely important, a new concept which I introduced here fairly at the end. Okay, question number 12 here is, create a linear inequality with both constant and linear terms on each side for which the solution is x less than equal to 7. So we need to work backwards from solution. That is the criteria, right? Let's see how to do it. So now the question is, we are given the solution which is x is less than equal to 7. We are looking for a linear inequality. So linear means mx plus b types. Okay. So what we can do here is that we can add the same terms on both the sides. We can add the same terms on both the sides, and so we can provide a linear solution. So in this case, we can just say x plus x is less than equals to 7 plus x. We're just adding x on both the sides. We can add a number also, right? We can also say, well, this becomes 2x. We can also add a number, let's say 3. So what you can do here is kind of important to write. You can add or subtract same term both sides. So in that case, inequality is maintained and you can get many different solutions. So 2x plus 3 less than, this becomes x plus 10 is same. So that becomes your solution. Does make sense to you? So you can always add or subtract same terms on both sides of the inequality just as you work with equations and get your solution. Here is the last question for you, which is solve 3x squared times x squared minus 8 plus 6x plus 10 less than 4x to the power of 4 minus 6x times 4x minus 1 plus 9. I'd like you to pause the video, solve it, and then look into my solution, which seems to be very complicated. What we are going to do now here is quickly expand and simplify. So when I multiply by 3x squared, I get 3x to the power of 4 minus 3 times 8 is 24 x squared plus 6x plus 10, and on the other side we have 4x to the power of 4 minus 24 x squared minus, and minus becomes plus 6x plus 9. Okay, so let's bring all the terms together. So we have 3x to the power of 4, and here we have minus 4x to the power of 4. Then we have minus 24x squared. We have plus 24x squared. That cancels. Good job. Plus 6x minus 6x. Excellent. Plus 10 minus 9. And that should be less than 0. So that's good. So basically, we have this as x to the power of 4. These two terms cancel. This gives us 1. Right? So we had 10 here, and what we get is 10 minus 9, which is plus 1, is less than 0. So that is what we get. However, we know x plus 1 is always positive. Sorry, this was negative, right? Okay, so that is okay. So I didn't notice. So this is okay. It is minus x to the power of 4, right? Minus x to the power of 4. Okay. So basically we have minus x to the power of 4. So we can just multiply by negative. So we get x to the power of 4 minus 1 is greater than 0. That makes sense. So this becomes x squared plus 1 times x squared minus 1 greater than 0, which we could write as x squared plus 1 times x plus 1 times x minus 1 greater than 0. Correct? So we have a factored form. That is good. And now we can actually analyze and find the solution. So that is it. Now, to analyze, we'll make a table. And in this table, we have critical numbers which are at x equals to minus 1 and x equals to plus 1. So those are our zeros. So we'll take test points. Test points could be minus 2, 0, and 2. And now we'll write down our factors: x squared plus 1, x plus 1, and x minus 1. X squared plus 1 will always be positive. X plus 1, when you put minus 2, will be negative, but these will be positive. For x minus 1, these two will be negative. And when you add them up, what do you get? You get positive here, negative here, positive there. So that is what you get. And we are looking for something greater than, that means these two intervals. Perfect. So check here, we change the sign because you multiplied by negative. Is that clear to you? So we are looking for something greater than 0. So those are the intervals. So we have our solution, which is, let me write down here, since it is greater than, the points are not included, from minus infinity to minus 1 and from 1 to infinity. Is that clear to you? So that is how we are going to get our solution. Let me write down the solution here on a number line. So we get it between minus 1 to infinity or from 1 to infinity. So that becomes the solution. So if x values are very large, in that case, we do get answer for this. 0 is not the solution. So you can do the 0 test. If I write 0 here, these two terms are 0, and we get 10. And if I write 0, all these terms are 0, we get 9. And we know that 10 is less than 9 is incorrect. And therefore, 0 is not the solution. So from 0 test, we found that this is correct. So I hope you got the concept of 0 test to check. Also, almost at the end, we'll elaborate on this in the next video. So what you have seen here in shortcut is that if the question is complicated, it's a good idea to check whether 0 is a part of solution or not. We clearly see that in our solution, 0 is not a part of solution and can be checked from the equation. Perfect. So that is the end of this particular video. However, let me remind you that these are tough times. We are going through a very tough time here, and you need to stay safe home. However, you can always explore our videos. Also, send your request on any questions in mathematics. We'll try to help you out in the best possible way. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time, and I hope with this you learned something about polynomial inequalities. We'll take up a test question on polynomial inequalities to practice what you have learned here. Thank you once again, and all the best.